Every single second of our lives, there's this invisible force at work all around us. It's the reason we can walk, the reason our cars can drive, and even why things eventually stop moving. Today, we're going to pull back the curtain on this unseen force, friction.
So let's just start with a simple question. What's that one invisible force that basically governs everything that moves? We take it for granted every day, but without it, our world as we know it would just not work.
And the answer, of course, is friction. At its very core, it's a pretty simple force that pops up whenever two surfaces are touching, and its one and only job, to push back against motion. It's kind of like the ultimate resistance fighter in the world of physics.
This brings us to the #1 rule of friction, and it's a big one. It always pushes in the exact opposite direction of motion. So, if an object is moving to the right, friction is pushing to the left. That's it. No exceptions. It's a constant, perfectly opposing force. Okay, so if friction is always pushing back and slowing things down, you have to wonder, where does all that energy of motion actually go? It can't just vanish into thin air, right? Well, it doesn't. It gets converted into something else, and that something else is heat.
It's a pretty straightforward swap, really. The kinetic energy, that's the energy of motion, gets transformed directly into thermal energy, which we just feel as heat. So every single time friction does its job, it's generating a little bit of warmth.
And you know what? You've felt this a million times. Go ahead, try it right now. Rub your hands together really fast. That warmth you're feeling? That's friction in action. It's the exact same principle that explains why a car's brake pads get scorching hot after you brake hard.
But hey, friction isn't just for solid stuff rubbing together. It also happens when objects move through fluids. And by fluids, I mean things like air or water. This special kind of friction actually has its own name. We call it drag. So what is drag? Well, it's just the fancy name we give to friction when it happens in a fluid. You know that feeling of the air pushing against you when you're riding a bike? Or the water resisting you when you're trying to swim? Yep, that's drag.
To really get why drag is so important, just imagine dropping something. If there were no air, like in a vacuum, gravity would just make it speed up and up and up forever. But here in the real world, the drag from the air pushes back, and that pushback actually slows down its acceleration.
And the rule here is super simple. The faster you go, the stronger the drag gets. It's an easy one to remember. That's why sticking your hand out of a car window feels totally different when you're going 10 miles per hour compared to 70. The pushback is way, way stronger.
Okay, so this whole drag gets stronger as you go faster thing leads to something really cool, a kind of natural speed limit for anything that's falling. We call it terminal velocity, and it's the reason a skydiver doesn't just keep accelerating all the way to the ground.
Let's break down how this happens. When a skydiver first jumps, the downward pull of their weight is way stronger than the upward push of drag. But as they fall faster, that drag force gets bigger and bigger. Eventually, they hit a point where the upward force of drag perfectly balances the downward force of their weight. At that exact moment, they stop accelerating, and they've reached terminal velocity.
So to put a nice, neat definition on it, terminal velocity is that constant speed a falling object hits when the push of drag equals the pull of gravity. The forces are perfectly balanced, so acceleration drops to zero, and the object just keeps falling at that one maximum speed.
All right, let's bring this all back down to Earth. Because friction isn't just some cool physics concept about skydivers, it is absolutely critical for something we do every single day, stopping a car. Honestly, without it, braking would be completely impossible. It's a lifesaver.
So stopping isn't just one thing. It's two parts. First up, you've got what's called thinking distance. This is literally the distance your car travels in the time it takes for your brain to see a problem and tell your foot to hit the brake. And things like being tired, distracted, or under the influence can make this distance dangerously long.
And then, part 2 is the braking distance. This is the distance the car covers after you've slammed on the brakes. And this is where friction is the absolute star of the show, the friction between your tires and the road. How well it works depends a lot on your speed, if the road is wet or icy, and even the condition of your tires.
So you put them together and it's a pretty simple equation. The distance you travel while you're thinking, plus the distance you travel while you're braking equals your total stopping distance. You've got to account for both.
Now here is the most important thing to remember for safety. This relationship is not one-to-one. Because a car's energy increases with the square of its speed, doubling your speed doesn't just double your braking distance, it actually quadruples it. Yeah, you heard that right. Speed has a massive impact.
Okay, so let's do a quick knowledge check here. It's really important to know what affects your reaction time versus what affects your car's ability to brake. So which one of these factors increases your thinking distance?
And the answer is C, alcohol consumption. Why? Because it slows down your brain's reaction time, which directly makes the distance you travel before you even hit the brakes longer. Things like worn tires or a wet road, those affect the physics of braking. That's the second part of the equation.
All right, so let's just quickly wrap up what we've covered. We've seen that friction is this fundamental force that always opposes motion. We've learned that it converts that motion into heat. In fluids, we call it drag, which is what gives us the concept of terminal velocity. And most importantly, friction is the force we all rely on to stop our cars and stay safe on the road.
And this leaves us with a really interesting final thought, a bit of a paradox. Friction creates drag, it wears things down, it always tries to slow us down. But at the same time, without it, we couldn't even walk. Cars couldn't grip the road. Our entire world just wouldn't work. So it makes you wonder, in the grand scheme of things, is friction more of a help or a hindrance?